Hi, guys. Hi, Ross. Welcome to RITSec. Announcements. Okay, please sign in. You guys know the drill. Go to Discord. Join the Discord if you don't have the Discord. They're not in order. We good? We good? All right. Oh, I'll go back. Please sign in. Yeah. Sign in category, general meeting, React. Okay. Raise your hand if you need help. You good? No? We're good? We're all good? Let's go. Okay. Check the calendar. You guys know. Calendar.rtsec.club. Okay. Join the mailing list if you're not already on that. Similar to that, it's mail.rtsec.club. Are we good? We're good. Meet the sponsors, clap it up. Come on, you know. Keep going. Oh, yeah. Keep going. Oh, yeah. Oh, yeah. Okay. Follow. Excuse me. Follow our social media. We're making posts on there now. It's really nice. Thank you, Sophia. Is she in here? Oh, yeah. Clap for Sophia, please. Yeah. Okay, we have a new feedback form. RITSec feedback. All right? You guys should do that. Give us feedback. We need to improve. It's RITSec Club now, I think, right? RITSec, yeah, okay. RITSec Club. Underscores on both sides, I believe. Oh my goodness, I'm sorry. Like I was saying though, feedback. Okay, I'm gonna do the announcements for this. We now have UB Blue Team sign up. You want me to do it or do you want to do it, Jason? Come do it, Jason. Everybody clap for Jason, please. Oh yeah.
I'll let the talk. All right, hello. One of the first competitions that you guys will be able to do as a blue team this semester is UB Lockdown, happening in Buffalo on October 15th. Note, this is homecoming weekend. If your parents are going to come and they want to see you, kind of sucks if you're in Buffalo and they're in Rochester. So keep that in mind when you're signing up. That's the form to fill it out. You need a full team of 6. Pick a team captain. We'll take care of the paperwork stuff later, but we don't have the bandwidth to handle partial team signups. So find some friends, make some new friends, get your team signed up. First come, first serve. It'll be great. We're going to have a fun time. Please do it. Thank you very much.
It's so fun. Is Jacob Dahl here? No? Okay. IRSec Blue Team signups are open. You guys should do that. It's our school Blue Team comp. I think Jacob Dahl gave you the spiel before. Yeah, do that, please. It's a good time. You don't have to have a complete team. We'll pair you with somebody if you don't have a full team. It's a fun time. We also have IRSec Blue Team workshops because I know a lot of people don't necessarily know how to Blue Team, so we teach you. So, first workshops, 10-1 at 12, and Intro to Competitions is the topic. Fun time. You good? Okay, we're good. Also, IRSec White Team signups. If you don't happen to make it on Blue Team, you can get on White Team. It's even more fun. You get to run around and deal with the Blue Teamers. Sign up. We good? Everybody got the QR code? Let's go. Okay. Okay, today...
It was announced today, so we forgot to put them in the slides. We have 2 new A-board positions opened up, so that's positions that put you on a track towards E-board. One of them is junior tech lead. That's where you're working with me, and we work on creating the demos. Hopefully you've been doing the demos every week. The other one is the junior ops lead. That's where you're actually maintaining our server infrastructure. We will send out more information about that. There's stuff in announcements about it. If you're interested, you can contact myself or Malik and learn more.
Thank you, Alex. Okay, today we'll be having Intro to Networking with Professor Weissman. Good.
Testing, 1, 2. How come your mic was louder than mine? Can I switch? Testing, 1, 2. Am I just not hearing myself loudly? Okay. Maybe I have to be over there. Okay. Let's just check my stream. That's your cue. No, go back. All right, how is everybody doing today? Good to see everybody. Some current students of mine, some former students of mine, some future students of mine. In addition to the Twitch stream, I am streaming on LinkedIn Live right now through a LinkedIn event, and I've already got confirmation that there are people from India, Silicon Valley, and other parts of the world that are joining us here today. So welcome to everybody, both near and far. My name is Jonathan S. Weissman, and I am a senior lecturer in the Department of Computing Security here at RIT. I also teach courses for iSchool, so you might have me for sysadmin 1, sysadmin 2, net services, intro to routing and switching, advanced routing and switching. I do a bunch of courses, so as a CSEC student, or even as a non-CSEC student, you'll see me in many different venues. For those of you that don't know or haven't gotten the opportunity to meet me just yet, I do have some introductions that I want to make available to you. I do appear on the local TV news as well as other news channels around the country. Every time there's a related cybersecurity story for the general public, my specialty is taking all that techno stuff that we talk about and turning it into something that the general public can understand. Some of the things I've talked about, as you might imagine, Russia, China, Apple, Facebook, DDoS, ransomware, things along those lines. So you'll see me from time to time on different stations, both again locally and nationally as well. I also appear on local radio stations and talk shows. Anybody ever listen to Radio 95.1? So I'm usually on with DeTulia and Moran, and there was a great show, the old David Reed show, that I was a regular on anytime there was anything related to networking and cybersecurity. That was unfortunately canceled a little while ago, and they replaced it with a show that's infinitely worse than that show, but I'm not going to get into that right now. They don't do any networking or cybersecurity stuff. That was an accidental tap, but it's good. You can keep it right over there. I also do a lot of articles, both as a person who's quoted in terms of networking and cybersecurity stories, as well as writing articles, both near and far, local papers, as well as national papers like Discover Magazine, Martha Stewart Magazine. So you'll see my name in action in the media. In fact, as an undergrad, I was actually a communications major before I turned to the side of networking and cybersecurity. So being able to do these media interviews is sort of allowing me to live out a dream that never came to fruition. My original dream was to be a news anchorman, and I guess I get to do that along with the networking and cybersecurity stuff that I do on a daily basis. Sometimes I'm on the front page of newspapers like that. While at home, stay safe in cyberspace. I'm also the author of 2 Network Plus books that have been updated twice, as well as a new book on Security Plus. So if you're interested in certifications, please come talk to me. I can help you. I can get you the resources. As RIT students, you get my books for free through the O'Reilly platform. I don't want your money. I just want you to take my words and pass the exams and do stuff with your certifications. Speaking of certifications, I do have 44 high-level industry certifications. I'm never not studying for a certification exam. What I like to say is the learning process never ends. If you ever think that, oh yeah, it's networking and cybersecurity stuff, you're going to know everything and you're done and you're ready to stop learning, you're going to be obsolete and undesirable in a rather quick amount of time. So cybersecurity specifically, and networking of course, requires you to constantly reinvent yourself and basically say that, oh yeah, all that stuff that I learned back then is old and obsolete and not relevant anymore. and I've got to learn the latest and greatest, and certifications are one of the ways that I stay current with industry. Another way is through industry consulting. I do consulting for local businesses and individuals as well, and I love bringing stories from the field back into the classroom. And when you think about it, I don't want to throw anybody in the bus, but teaching the courses that I teach, and I teach a wide variety of courses here, you really do need the industry experience to be able to explain it properly and stay up to date with what's going on in that proverbial real world. So that's one of the ways that I stay current, my consulting, the industry certifications. But my biggest passion, we're doing some coordination where when I go like that, it means he advances the slide. I think maybe like with the touch screens, 2 means go back, but we're not up to that point yet. My biggest passion out of all of my loves in the world is teaching, and if you've been in one of my classes, I hope that I conveyed that to you. And as such, I've won 11 teaching honors and awards, including the 3 biggest here at RIT over the last few years, things that I am the most proud of. I was also recently inducted as an IPv6 evangelist into the IPv6 Forum Hall of Fame. The IPv6 Forum is a leading body of certification for IPv6. Today, we will be talking in the world of IPv4, but I do teach a special IPv6 class that you can take over the summer. If you want details on that, see me after. And I do encourage you to follow me on social media. Connect with me. You don't have to follow me on LinkedIn. Connect with me on LinkedIn. Those of you watching me on LinkedIn Live right now know that I've got 30,000 contacts, and I post dozens of networking and cybersecurity articles on a daily basis. And that is another one of the ways that I stay current. You need to have all these ways to stay current. So if you connect with me on LinkedIn, you'll be able to read the articles, and you'll be able to read them either case, but you'll be able to interact. And I want to make my network of 30,000 available to you. I've hooked up students so many times with jobs and contacts, and I guess that's a different form of networking when you think about the word. But it's very important to market yourself, and I'm a big advocate of that, and I can help you do that for the low cost of $0.00. So connect with me on LinkedIn and follow me on the other socials, Twitter and Instagram, CSE Prof on both of them, just like my license plate that you see here and you might have seen in the parking lot. In fact, over the summer, somebody saw me driving on the Thruway and posted it to a Discord channel, and I was quickly identified. So definitely connect with me on the socials, and if you want to see any of my previous media appearances, they are on my YouTube channel, Weissman52 on YouTube. All right, enough of that. Any questions or comments before we go on? I forgot to click for you there. Okay, next. Okay, we've got a stacked agenda right over here. Let's get right to business. The plan is to go through all of these and see how much you remember through a Kahoot fun extravaganza. No cash prizes are awarded, but you get the bragging rights. Starting off with 2 funny stories. So over the summer, my family and I live not too far from here, about 10, 15-minute drive in Brighton. And there were a bunch of families that were moving into the neighborhood, and we wanted to become friendly with some of them. They had kids, our kids' ages. So we befriended a few of them in Wegmans and 12 Corners and the other areas that we find ourselves in. And there was this one particular family that we were really, really excited about, that they moved into the community. So my wife made them a care package, and there was like chocolates and chips and all that good stuff in there. And she said, Jonathan, go ahead and deliver that package to the Smiths. This guy named Bob Smith, head of the family, and I was talking to him at Wegmans earlier that day. So my wife gave me this package to deliver to Bob Smith, and I remembered his name was Bob Smith, and I didn't know that a few houses actually did go on our block recently, but I wasn't quite sure which house the Smiths moved into. So what I did was, I'm also a musician, so I got my amplifier, 500-watt amplifier out, and microphone, and I didn't have to scream because I jacked up the volume to 10, but it was 11:30 p.m. I said, hey, Bob Smith, which house did you live in? Because I didn't know which house he lived in. The whole block had a bunch of families that recently moved in. I didn't know which one was him, so I just had to scream it out, had to shout it out, had to broadcast it out. That was the only way I could get his attention. I got his attention, but you know whose else attention I got? Everybody else on the block. I woke up my kids. My wife had a hard time putting them to sleep that night. I woke them up. She was pretty pissed off at me. People on the block were screaming, shouting profanities at me. Do you know what time it is, you stupid moron? And I was the most hated person on the block, but it was worth it. It was worth it because I got Bob Smith's attention. And he very discreetly walked over to me on the stoop of my house, stoop of my porch, and he said, it's 123 Main Street, and then he walked very quickly back to his house because he didn't want to be associated with me. So later that night, I think it was after midnight, after I pilfered a few of those chocolates and ate them myself, I brought that care package to the Smiths and delivered that. That's story number one. Oh, no, still go back. What do you think of that story? Is that Sarah? What do you think of that story? It's a wild story, but I've got an even more wild story. The even more wild story is about my mom's candlestick holders. I'm originally from Staten Island, New York. Anybody here from Staten Island? Impractical Jokers, Wu-Tang Clan? So I am originally from Staten Island, New York, and we did a bunch of traveling over the summer. We went to my parents' still in my childhood home in Staten Island, and my wife's parents and family who are still in her childhood home in Philadelphia, Pennsylvania. You guys, by the way, know the difference between in-laws and outlaws? Outlaws are wanted? No, I like my in-laws. I love my in-laws. Wait a minute. What are all these streams? We have to edit these recordings after. I love my in-laws. So anyway, when we got back from one of these trips that we made, we were unloading the car, and I was lifting up the bags of my kids, Noah on the left and Jacob on the right. Actually, Noah on my left and Jacob on my right, and then they switch over there. And what happened was the bags were extra heavy, so I opened up the bags, and in Noah's bag was one of my mom's fancy candlestick holders, and in Jacob's bag was one of my mom's fancy candlestick holders, and I said, "What's going on, guys?" And they said, "Grandma, let us have them." And then I checked my email, and it's from my mom, and she wrote actually 6 emails in that trip we spent coming back, 6 hours from Staten Island. "Did you see my candlestick holder?" So I called her up, and I said, "Kid said you can have them." She said, "I didn't say they can have them. I said they can look at them and play with them." So she said, "Give me them back. Sabbath's coming soon. I need to have them to light Sabbath candles." So what I did was, I wasn't going to drive 6 hours back to New York City, so what I did was I put the candlestick holders in a brown box, and I Googled for the nearest UPS store to where we live. And I found one on Elmwood Avenue in Brighton, and I brought the candlestick holders in the brown box to the UPS store, and that UPS store sent it to another UPS facility, and that UPS facility sent it to another UPS facility, and all the way down until it reached my parents' home in Staten Island, New York. Is that an even more wild story? Okay. So I thought that stories are good before a networking lesson. Let's talk about the difference between local traffic and remote traffic. You're doing very well at that, by the way. Local traffic is where you've got the source, the sender, the originator of a message that's sending traffic directly to the actual destination. That's what we call local traffic in the world of networking, directly delivered. In the world of networking, we call remote traffic that you're not, you as the source, you as an end device, whether it's a laptop, a desktop, a phone, mobile device, whatever it is, where you're not delivering the traffic directly to the actual destination. You're going through some intermediary devices that we will be talking about in a second. Hey, there's a second over here. Didn't realize how quick that second was. 2 very important networking devices, of course. The first one on the top over there is something called a switch. The switch, think of the streets of a city where the different end devices, an end device is something that's the source or destination of traffic. The switch is just the series of streets. You know, you go along the streets, and you go to Wegmans, and you go to CVS, and you go to RIT, and you go to all the other places that you go to in this immediate area. That's what a switch is. It's connecting the end devices of a local city together. So think of the end devices, again, like laptops, desktops, these things called printers that, I don't know if you guys are old enough to know what they are. Mobile devices that can be plugged in, things along those lines. Those are the end devices like the buildings, the offices, the coffee houses, Starbucks, Dunkin', the banks. Those are the end devices that plug into the switch. So when you're in a city and you want to go from RIT to Wegmans, you go into the switch. RIT is going to be the source. Wegmans is going to be the destination. You want to go back to RIT, the roles actually flip. But the router doesn't connect end devices of the same city together. The router connects different cities or states or whatever breakup of the geography you want. Think of the router as you're driving on the highway and you want to go somewhere far, maybe from Rochester to Staten Island, New York. And you take one highway, and that highway leads you to another highway, and that highway leads you to another highway. Think of those highways that you're going through, leading you to other highways, leading to other cities, and in some cases, states. Think of them as the routers. But of course, when you get to your final destination, that's a good movie. Anybody see that? It's a series, Final Destination. Sorry for another day. When you get to your final destination, you're not just leaving the router. The router is going to connect you to the local city streets. There you've got another local switch. And you know that some streets can lead to other streets in the city. So yeah, switches can be connected together, whether it's a linear connection or a hierarchical connection. Switches can connect other parts of the city to other parts of the city. Now, wait a minute now. How does one get from RIT to Wegmans, from Wegmans to RIT, or other places along the routes here in Henrietta? How do we get to these places? How do we know where we are? There's got to be some logical identifier known as an IP address that represents a logical, software-assigned, hierarchical, and geographical address. What that means in a nutshell is that if you're using your laptop here, you're going to have a certain IP address that our DHCP, Dynamic Host Configuration Protocol, that's a story for another day, servers gave you. But when you go somewhere else and you're on somebody else's local area network, that respective network will have their own servers that give you a corresponding IP address. So they are logical and assigned through software, which means they change based on the networks that you're on, according to the hierarchical and geographical principles as well. You can trace where somebody is sending a message from, in most cases as far as their ISP, their Internet Service Provider, but the ISP will have logs of who is in possession of a certain IP address at any point in time. So the IP addresses change when you move from network to network, and in a lot of cases in the world of IPv4, which was the first form of addressing that hit the market, IPv6 has been slowly branching out since, more so than ever since 2015, when we in the United States and other parts of the world ran out of IPv4 addresses. That's a story for another day. But when you send traffic from an IP address, it will tie you in most places geographically, in some cases to the continent, in some cases to the state, in some cases to the city, and in some cases directly to your Internet Service Provider. Now, yeah, VPNs and obfuscation, we're not talking about that. This is the introduction to networking, not how to do really cool, funky things in networking. That would be a different presentation. So IP addresses consist of 4 numbers in base 10, separated by dots. That's why it's called dotted decimal notation. And by the way, that word decimal doesn't mean that dot. The dotted means the dot. Decimal means base 10 in this case. So for example, I've got an IP address on the board over there of 172.16.254.1. And each one of those numbers is represented by 8 bits underneath the hood. Everything is binary underneath the hood. So if you take a look, the 4 octets, as we call them, octets because they're represented by 8 bits, the 4 octets have a byte, an 8-bit pattern in base 2. That is really what's sent and received. 8 times 4 is 32. IPv4 addresses are 32 bits long, and they consist of 2 parts. The first part is known as the network ID, which means everybody in the same network, everybody on the same LAN, starts off with the same set of bits. It's always the first set. The next part of an IP address is known as the host ID, which is like a unique identifier, a serial number that's unique to each individual node. NODE, by the way, is a fancy word that means anything that has an IP address. Host is used in the same way. Any node or host has a unique identifier known as the host ID portion, which comes at the second part of the IP address. So what's the obvious question now if I'm telling you that the IP address consists of two parts, the network ID and the host ID? What's the obvious question you got to ask me? Right. How do you tell where the network ID ends and where the host ID begins? Where's the breakup over there? So you need something called a subnet mask. And that's an example. No, that's not a subnet mask that I want to talk about. This is. I was doing it wrong before. No, that's not a subnet. Well, it is a mask under the net, subnet mask. Subnet masks are represented in one of three different forms. If you look at the first column, this is something that you're going to be drinking on a cold Rochester evening coming up soon. You know, today we started in the 40s, and I don't think we're making it to the 60s today, first time. Trust me, in 2 months from now, when we've been in the teens and the single digits, and we get up to like 32 degrees, everybody's going to be walking around in shorts and flip-flops, and 32 degrees is the temperature at which water freezes, but everything is relative. Today, 49 was cold. We'll be praying for 49 in a couple of weeks. So where am I going with that? Oh, yeah, look at the label for the first column over there. That's something you're going to be drinking on a cold December evening in Rochester, apple cider. Cider stands for Classless Interdomain Routing. It's a way to represent how many of the 32 bits in the IP address are network bits. So if you take a look at the first example, /9 means all network devices on this particular LAN that have a cider notation mask of /9 have the first 9 bits as network bits, and they are always going to be the same. If you take a look at the second column, we've got the dotted decimal representation of the subnet mask, 255 in this case, .128.0.0. Because if it's /9, you've got 8 bits in that first octet. Highest number you can make with 8 bits is 255. And you've got the first bit of the second octet from the left, the most significant bit. That's the 128's column. That's the way that IPv4 subnet masks are configured. They are not configured with cider notation. They are configured with dotted decimal notation. But if you take a look at the last column over there, that's the actual binary representation of the mask. So here's how it works. When you take the IP address, and you take the 32 bits of the IP address, and you write them across from left to right, and then you write the subnet mask underneath. It's called a mask because it hides some things. If you take a look at the subnet masks over here, anytime there's a 1 in a position in the subnet mask, it means the corresponding bit in the IP address at that same position is a network bit shared by all devices on the network. And if a subnet mask bit is a 0, it means the corresponding bit in the IP address is part of the host portion. That's how we see the breakup. So if we want to figure out how this networking communication thingamajig works, we have to understand figuring out what network we're on. Because if a source has traffic for a destination and the destination is on the same network, the process is different than if the destination is on a different network. So if you take a look, I'm trying to think. I do have a pointer. Hang on a second. Come with lots of props. If you take a look at the IP addresses that are in the, and I just realized for the streams, you do not see this, right? All right, so maybe I'll just talk, I'll point for you guys in the room, and I'll just talk relatively as well. If you take a look on the left box on the top, 10001 is the source of the traffic, and Mr. 10001 wants to send traffic to Mr. 10002. If you take a look at the subnet masks in blue directly beneath those IP addresses in black, they are both 255.0.0.0. So what would the cider notation for that be? / what? How many bits are network bits in that example? Evan, help me out.
24? No,
8. 8, absolutely correct. No, he's fine. He's just looking at it backwards. 8, absolutely correct. So there are 8 bits in the network that this guy is on. We'll put this guy on hold, 10.0.0.2. We'll put him on hold for a second. So the first thing that the source of traffic does in any type of networking communication is you got to figure out what network you're on. You know why? Because if you're on the same network as somebody else and you want to send them traffic, you do it yourself, direct delivery, local communication. But if you're on a different network, you cannot send the traffic directly. You have to send it through one of those things called routers that we talked about earlier. So the source needs to ascertain whether the destination is on the same network or a different network. And then we got the binary in the middle right over here. If you take a look, black is black. In other words, base 10, 10.0.0.1 matches up with the 32 bits that you're seeing going across over here at the middle of the slide for those of you on the stream. And if you take a look at the blue matches the blue. 255.0.0.0 is 8 ones followed by 24 zeros. Now here's what happens. The logical operation that happens is AND, the A-N-D operation, which means, just going back to your math days learning about truth tables, if the first bit and the second bit are both ones, produce a 1 on the output. Otherwise produce a 0. So there's only one pattern that produces a 1, and that's where both of those bits are 1s. If you take a look in the first octet of the thingamajig in the middle of the slide, for those of you on the streams, if you take a look, there are 8 ones in this first octet's subnet mask, or this subnet mask's first octet over here, but there are only 2 ones coming down. It's because the 8s column and the 2s column are the only columns that have 1s in the IP address. And of course, all of those 1s are there in the subnet mask, but we're only bringing down the 1s in the 8s and the 2s column. If the subnet mask's second, third, and fourth octets are all 0s, there ain't no way to produce a 1 because those are guaranteed to be 0s. So what is this thing in orange right over here? In black, we've got the IP address. In blue, we've got the subnet mask. What would you say we've got in the orange? Who wants to help me out here? Right. Yes, go ahead. The network ID. The network ID. So the source says, I am on the 10.0.0 subnet. Wanted to make sure I didn't have an extra 0 there, or 1 0 too few. Source knows what network he's on. Now the source has the destination IP address, uses the source's subnet mask, and does the same logical AND process. Why does the source use the source mask and not the destination mask? Well, 2 reasons. Number 1, the source never will know what the destination mask is, nor does it care. Number 2, if the 2 devices are on the same network, the masks are going to be the same. So in this case, the source takes 10.0.0.2, performs the same logical AND process, comes up with the same network ID. And what does that tell the source? That tells the source that the destination is on the same network, and it could do some of that direct delivery thing. Source says, I don't need a stinking router. I could do it all by myself. Question so far? Well, look at this now. Made a little change here. I changed the destination IP address to 11.0.0.2. Change is in the first octet. And if you take a look right now, the resultant network ID is different than the first computation of the logical AND. So the destination, the source concludes, is on a different network, and the source realizes that it can't directly deliver the traffic. I'm going to need some help over here. So first things first. When we talk about, oh yeah, you got that IP address, how do you know the destination IP address? Arguably my favorite protocol, and I bonk around sometimes between the protocols, but it's usually DNS and ICMP, my favorite protocols of all time. More on that in another setting. But DNS does a lot of things. Most people just associate it with taking names and turning them into numbers, which is what it's most known for, but it does a bunch of other things as well. So if you take a look, a fully qualified domain name, like the name of a machine that a web server service is running on, usually named www, and a second-level domain like RIT, and a TLD, a top-level domain like EDU, you give me that name, and the DNS protocol will turn that into its corresponding IPv4, and in our case as well, an IPv6 address, and that's how you get the IP address. So you either have the IP address, somebody says, oh, can you ping me? My IP address is 10.0.0.2, or somebody gives you the host name, or you have the host name, you have the fully qualified domain name, and you're able to reach it. But there's still a problem here. The problem is, which device has that IP address at any point in time? Because a bunch of you have your laptops open right now, and you know what? You're using the RIT DHCP server, and we are very privileged here at RIT because we don't use that stupid RFC 1918 private address space. All of our addresses are public here in RIT. So all of our addresses will start off with the 129.21 prefix. So my point is, you could be using 129.21 whatever one day, and somebody else could get it a different day. So those addresses are software-based, they're logical, they're not permanent. So here's the obvious question now. Okay, I got that IP address, but now which device is in possession of that IP address? And that's where we start talking about things called the network interface card, which, by the way, hasn't been a card for a very long time. It's been a chip. I've tried to get industry to change the expansion of that acronym from network interface card to network interface chip. For some reason, people still insist on calling it a card. It originally was an expansion card that plugged into your motherboard, but even on desktops for decades, it's been a chip right over here. And by the way, don't, at least in my presence, say NIC card, because that'd be like saying ATM machine and PIN number. So the C does stand for card. The network interface card. And there's another type of an address we've got to introduce over here besides the logical, software-based, hierarchical, geographical IP address. We've got the media access control, the MAC address, which is physical, hardware-based. There's no hierarchy, there's no geography to the actual MAC address structure. It consists of 48 bits. It's written in hexadecimal notation. Depending on your operating system, you might see 2 hex digits separated by a colon or a dash. Operating systems do it differently. But if you have a NIC, your MAC address is not going to tie you to any company. Well, it will tie you to the company that made it, but it won't tie you to any ISP. It won't tie you to any entity like RIT. It won't tie you to anything except for the vendor of the MAC address, because the first 6 hex digits, the first 24 bits, those are known as the OUI, the Organizationally Unique Identifier. You have to register for that if you're a vendor of NICs. And you could easily do a Google lookup to see who made your NIC if Windows or any other operating system can't identify it for whatever reason, and they all can nowadays. But that uniquely identifies the vendor. The second part of the MAC address, this one is actually split down the middle. The second part of the MAC address represents the equivalent of a serial number, sort of like a host ID. It's also known as the device ID. Some people call the OUI the block ID. So here's a common misnomer. People say MAC addresses are unique and no 2 NICs will be made, and they're burned-in addresses, BIA, with the same MAC address. That's a misnomer. That's a fallacy. Companies actually do duplicate MAC addresses, but they're actually careful to not ship them to the same city or the same state, or in some cases the same continent. And as I'm going to show you in a couple of minutes anyway, it doesn't matter, because these MAC addresses are only locally significant. In other words, you could have the same MAC address as somebody else. As long as you guys ain't on the same network, there's no problem. If you're on the same network, it's a major problem. So the chances of 2 manufactured MAC addresses burned into NICs making their way onto the same network, when the companies are very careful to ship them to different city states and other jurisdictions, highly unlikely. Still, still an oddball possibility. So now, if we think about this whole business of IP addresses and MAC addresses, remember I said you have your laptops open right now. You've been assigned an IP address from our server here at RIT. You go to some other location, your IP address will change. What can you say about your MAC address compared to here, compared from here to somewhere else? What can you say about your MAC address? It's going to be the same. It's very good. It's going to be the same. So your MAC address never changes. Yes, I could talk about spoofing and all that good stuff. This is just an intro to networking, so we're not going to go down that dark, dirty path just yet. So here's a little story. Here's a little story about host A that wants to send traffic to host B. This is what I call the scoreboard. In order to send the traffic, you don't need 1, you don't need 2, you don't need 3, but you actually need 4 addresses. You need 2 MAC addresses, one for the source and one for the destination. And you need 2 MAC addresses, one for the source and one for the destination. The MAC address in this context will uniquely identify who has possession of an IP address at any point in time. Think about a restaurant. Testing 1, 2. Think about, whoa. I've been teaching since 8 a.m. today, bear with me. Think about a restaurant where the restaurant is identified by the name of the restaurant and the address of the restaurant. And there's this really fancy table number 5 that everybody's trying to get a reservation for. You can't just call up the restaurant and say, oh yeah, I want to talk to the person who's at table 5, because the people at table 5 change as the day progresses. So think of table 5 as the IP address, but the actual identifier of the party that's at that table at any point in time as the MAC address. Do you see how the MAC address lends a device to an IP address? And that's why both are needed. So in our little story over here, the source, of course, knows what its IP address is. The source, of course, knows what its MAC address is. I'm just using fictitious MAC addresses over here. So I got 12 A's going across left to right for the source MAC address. Source knows what the destination IP address is. How does the source know? Either DNS or it's going to be manually given the actual IP address. But the problem is the source doesn't know what the destination MAC address is. How would it? It's not hierarchical. It's not geographical. There's no protocol like DNS to magically give us that MAC address, or is there? And there actually is. There's a protocol known as ARP, Address Resolution Protocol, which consists of 2 types of messages. There's an ARP request and an ARP reply. The ARP request is always a broadcast, which means the switches send the broadcast out of all ports except the port on which the message originated, and that broadcast will go from switch to switch and hit every end device in the network. It's very disruptive. It's terrible for the bandwidth. It's terrible for processing loads. But you know what? If host A needs host B's MAC address, it's the only way to do it. It's the only way to get host B's MAC address. How? By interrupting all network activities, getting every device on the network to read a frame up until the very last field and value, where every device in the network but host B here says, oh crap, you just wasted my time. It's wasteful, it's bothersome, but it's how host A gets host B's MAC address in this context. Host B, when he sees, oh yeah, that's my IP address, and then you look at this on Wireshark. Wireshark will put it in nice human-readable English. Who has 10.0.0.2? I need your MAC address. So every device on the network, if there are 20 switches with 20 devices plugged into each switch, and one of those devices sends an ARP request, the other 399 devices will actually hear that ARP request. And every one of those 399 except one will say, you just wasted my time. I'll never get those milliseconds back. But the one whose IP address is being sought at, or the one whose IP address we know that says, oh, if you're 10.0.0.2, I need your MAC address, that's the device that's going to say, oh, I'm going to go ahead and send an ARP reply. And that's exactly what's happening over here. Host B sends an ARP reply, which is a unicast message. What does that mean? It means one source and one destination. I'll show you a little trick that the switches do. But the switch is able to just send that unicast ARP reply back to host A's interface and eventually to host A without bothering everybody else in this topology. Does that sound familiar, that story? So if I knew Bob Smith's street address, or I knew Bob Smith's name at least. I knew Bob Smith's name, but I didn't know his street address. I did the only thing I could do. Yeah, I woke up my kids. I woke up all the kids in the neighborhood. It put me on the other side of endearment to a lot of people in the neighborhood. But I'm fine. I got Bob Smith's attention, but Bob Smith didn't shout back at me or bring out a 500-watt amplifier. What did Bob Smith do? Bob Smith walked discreetly to me, so I'm the only one who saw and heard Bob Smith. That's an example of unicast traffic. And now with the ARP reply, the destination MAC address in this example is all B's. And now host A can send whatever traffic host A's got for host B, because in the frame, if it's a wired LAN, it would be an Ethernet frame. If it's a wireless network, it would be an 802.11 frame. Whatever the infrastructure is, now we can fill in the destination MAC address. IP addresses are in the layer 3 packets, and the traffic moves from source to destination. Here's a little of a schematic of a switch. The switch contains another table. And by the way, after the ARP completes, as you might imagine, there is caching. So if the host needs to send traffic again to the destination, it doesn't send this broadcast. It retains that information in an ARP cache for a specific amount of time. And that way, future communications don't involve bothering everybody else in the neighborhood, just like I remembered where Bob Smith was until I went to sleep and then woke up the next morning and I forgot because that ARP cache had been emptied in RAM. But in this example over here, the switch has a different type of a table. The switch has something called, and it goes by a few different names, SAT, source address table, MAC address table, CAM, content addressable memory. They all mean the same thing, but here's the underlyings. It's called a source address table because when a device sends traffic into the switch looks at the source MAC address and says, I know where you are. That's why it's called a source address table. So when students talk to me in my classes and I ask them what their names are, I learn their names a lot quicker than the students that don't talk as often as the other students. So just like I learn your name quicker if you talk to me, the switch learns quicker if you talk, you send traffic into the switch. Switches are transparent in this context. Now, they could be the source and destination of traffic, but they're not in the story over here. They're the source and destination for SNMP, Simple Network Management Protocol, SSH, Secure Shell, and other things. We're not getting into any of that. But look at these tables over here. After each device has sent traffic, the switch knows where Fred is, where Barney is, where Wilma is, where Betty is, because their corresponding MAC addresses are associated with the ports on which their traffic, their frames, were heard on. And that's how the switch is able to take the ARP reply and only send it back to the port that host A is connected to, because it learned where host A was from the ARP request. And now for the ARP reply, it doesn't have to flood out that ARP reply to all of the ports, not knowing where host A is. Host A said, I'm host A, this is my MAC address, this is my port, and if you have any future communications meant for that MAC address, you know which port to send it out of. That's how the switches do their business. And if you take a look, after the MAC address table has stabilized, anytime traffic, in this example over here, Fred has traffic that Fred is sending into the switch right over here for a destination of the Deuces Wild. Looks like Barney over there. So the switch knows where Barney is. The switch knows that Barney is in Fast Ethernet 0/2. What that means, I'll tell you another time. Port 2. And because of that, the switch only sends the traffic out of Barney's port, not the other ports. That would be bothersome for the other devices. It would also be a security vulnerability that we'll talk about another time. So if you take a look right over here, as soon as the frame enters a port, the switch tags you in its table and RAM, and it knows your MAC address based on the source MAC address in the frame, and it associates your MAC address with the corresponding port that you're on. Remote communication, though, is a different story. Because remember, remote communication, you don't deliver the traffic directly to the destination. With remote communication, you give it to a router. And you know what? All you care about is getting it to the router. Your router, your default gateway, does not care about the destination. The only thing your router cares about is getting it to the next router. And the only thing that next router cares about is getting it to the next router until it reaches the actual destination LAN. So let's tell a little story about remote communication over here. The source of traffic is going to be one of these devices in the lower left in the 12.0.0.0/8 subnet. That means every device on this LAN starts off with a first octet of 12. That's the network ID portion. And the other three octets, octets 2, 3, and 4, are host octets. They have to be different in totality. Side note that all host bits, no matter how many you have, they can't all be zeros. That represents the network ID. And they can't all be ones because that represents a form of a broadcast address that hasn't been used in decades, but we throw those two addresses away. Any other pattern of the zeros and the ones for the host portion is a valid host portion. So in our example, I've put a source IP address of 12.0.0.1 and a destination IP address of 14.0.0.1 all the way up there in the right corner on the top. Source knows what its IP address is. Source knows what its MAC address is. In order to save space, I'm going down to 2 hex digits for the MAC address, not obviously drawn to scale. So we're just going to use double letters for our MAC addresses. So the source, Mr. 12.0.0.1, let's say it's one of these PCs down here, connected to that little switch, has to decide whether traffic is local or remote. We went through that whole business with the ones and the zeros and the logical AND process. Source knows that the destination is on a different network. So you know what the source needs to do at this point? The source needs to look in its TCP IP configuration for the default gateway IP address. The default gateway is a router interface that's connected to your LAN, that's responsible for taking traffic meant for other networks off your network and bringing traffic from other networks back on to your network. So the host sees a particular default gateway IP address, but wait a minute now, the source needs what at this point? Needs a destination MAC address. But it doesn't look for the destination MAC address of 14.0.0.1. It looks for the MAC address of its default gateway. And how does it do that? ARP. So if you're sniffing in Wireshark, the ARP request, which is always a broadcast, will say, if your IP address is, and let's just make up this default gateway IP address, if your IP address is 12.0.0.99, I need your MAC address. All the devices in the LAN are going to hear it, but the router interface is the only one that's going to say, that's for me, and send an ARP reply back to the host. Now look what happens. Watch this table over here. In this case, the router says, my MAC address is BB. So the source takes the packet with the source IP and destination IP addresses and puts it in a frame with a source MAC address of its MAC address, AA, and a destination MAC address of BB, which is the MAC address of its default gateway. Everybody still with me here? All right, so the frame comes into the router interface. It comes into that R2 interface down here, router 2 interface down there. Router looks at the frame and says, yes, that's my MAC address. Let me strip off that frame. Wait a minute now, that's not my IP address that I see in the resultant packet. So the routers also have tables, and the router looks in its routing table. There's a simulation, a scaled-down version of what an actual routing table looks like. The router says, look, I am not 14.0.0.1, but I know that if I have traffic meant for the 14.0.0.0/8 subnet, I'm going to send it to, if you take a look right over here, I'm going to send it to R1. So R2, D2, says now, I got to get R1's MAC address of the interface that I'm directly connected to. And if they are Ethernet interfaces, you will actually see an ARP request and reply if they're not cached already, which they probably will be for like ever, because routers are always in communication with each other. But if you clear the ARP caches, you'll be able to capture the ARPs. Point is that the top, we'll just use words like top and bottom over here, the top interface of R2 will send an ARP request looking for the MAC address of the R1 interface that it's directly connected to. Get an ARP reply back. Now look at this. The packet is still the packet, but now it's reframed in a new outer encapsulation. CC represents the top interface of R2, which is the new source MAC address. And DD represents the left interface of R1 that's receiving this new frame with the original packet and all the other stuff inside of it. R1 says, yes, that's my MAC address, DD, but wait a minute, I'm not 14.0.0.1. So R1 looks in its routing table. Look at R1's routing table. Who does R1 have to send the traffic for to get to the 14 network. Who does he have to send the traffic to? Which router? It's like R4, right? It's got to send it to R4. So once again, assuming nothing's cached, ARP request and ARP reply. And now, if you take a look, new source MAC address EE, which represents, let's say, the right, that would be right, the right interface of R1, and the new destination MAC address FF, the bottom left interface of R4. R4 again says, yeah, that's my MAC address. No, that's not my IP address. Looks in its routing table, and what does R4 say? R4 says, wait a minute. I don't need to send this to any other router. I could service this traffic myself because one of my interfaces is directly connected to that destination network. So that interface on the top of R4 will send an ARP request looking for the MAC address of the actual destination, 14001. Get an ARP reply back, and look at this, another time, a new frame re-encapsulates that existing packet. So GG will be the top interface of R4, and HH will be the MAC address of the actual destination, 14001. Who says, yes, that's my MAC address, and for the first time in the story looks at the destination IP address in the packet and says, yeah, that's my IP address, and then opens up the rest of the stuff that's in between. And that's how remote traffic works. So if my mom's candlesticks were in Rochester and I had to get them back, I wasn't going to directly deliver those candlestick holders at least back myself, although it's always nice to visit my old stomping grounds in New York City. But what did I do? I found the nearest UPS store. In other words, I looked up my TCP IP configuration. I found my default gateway. What did the UPS store in Brighton do? They didn't deliver the candlestick holders to my mom. They found another UPS facility to send the traffic to, and they kept the propagation of my mom's candlesticks, probably a phrase that's never been uttered before, to my parents' home in Staten Island, New York, until it was serviced by a UPS facility, put it on a truck, sent her the candlesticks. So if you take a look, with every hop, which means a router or a network that you're passing over, ding, 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 there you go. With every hop, the packet and everything that's inside the packet is removed from the whole structure, which is encapsulated inside of the frame. And every hop, when you ever move from network to network, router to router, it's a new frame with a new source MAC address and a new destination MAC address. And now you can understand why I was saying earlier that MAC addresses are locally significant. All right, a little bit more. Programs and more, some terms that come up from time to time. There's a lot of confusions of these terms. You know those ones and zeros that are coming into our machines. The way they go in and out of the machine is through the NIC, the network interface card. But logically, the way in and out of a machine, the actual communications, has got to be through something called a program, which are lines of code that follow algorithms to solve problems or accomplish tasks. That's the way in and out of a machine logically. A program, oh, actually, ding, ding, forgot about that. There we go. A program, as we said, is lines of code compiled down into machine-level language so the CPU can understand them, that solve problems or accomplish tasks. A service is a special type of a program. A service is a program that runs in the background independent of a sign-in. Think of a web server service that when you reboot the machine, the service starts up without having a user needing to sign into the machine. In the world of Linux, we don't use the term service for that. What do we use? Daemon. But you know what? In the world of Linux, there is a term service. In the world of Linux, service basically means a program, a command that calls a script that launches a daemon. Leave it up to Linux to redefine service from the existing terminology that Microsoft originally established. A process is a running instantiation of a program, and a thread is the smallest unit of a process that's running. Why is that all important? Why is that important? One more. The way into a machine physically is through the NIC, those ones and the zeros, whether it's a wireless NIC or a wired NIC. The way logically in is through a program. But you know what? How do you get into a program? How do you get into a service? Something known as a port. anytime you hear the word port, think of some number, some logical representation of an endpoint. For example, in this building, we have these inhabitants of this building. Guy down there checking his snail mail, his name is Frank, and the lady up there, her name is Helen. They both live in the same apartment building. So if you want to write each of them a letter, it's the same address, 123 Main Street or something along those lines. But how does Frank get his mail and how does Helen get her mail? Well, for Frank, you have to write what apartment he lives in, which is 21 in this case. And for Helen, I believe she lives in apartment number 80. So if on a single machine, you've got an FTP, a file transfer protocol server running. And by the way, server means software. Everybody thinks servers are hardware. Servers are the software services that are running. People just turn that into the physical representation of the machine that's running them. But if you've got two server services, let's say you've got an FTP FileZilla server on a machine and you've also got an Apache web server. How does the traffic for the FTP server get to the FTP server? How does the traffic for the Apache web server get to the Apache web server? Same MAC address, same IP address. We need some other form of identification, and that's this thing called a port, a logical representation of an endpoint. So when you start a service, that opens up a port. When you stop a service, that port, that numeric representation is closed. So his name, Frank Thomas Peterson, that's his full name. That's why he lives in apartment number 21, because FTP servers send and receive on port 21. Her full name is Helen Teresa Thomasina Parker, and web servers that don't do TLS, that don't do encryption, they listen and they send on port 80. I heard since the story started, she got married to some guy whose last name starts with S. So now she's Helen Teresa Thomasina Parker Simons, and they moved. Anybody know what apartment they moved to? 443, right, TLS, absolutely, Transport Layer Security. There are different categories of port numbers. Well-known port numbers are numbers that server services listen on, with the exception of one I'll teach you about in my net services class. They're all server port numbers. FTP servers 21, SSH 22, DNS 53, DHCP servers 67. Well-known ports. When you're talking TLS 443, when you're talking about the client ports that are opened up dynamically, web browser wants to send traffic to a web server. The web browser will open up a port in the dynamic range or even in the registered range. Some companies like to register for port numbers. This is more of a thing of the past, to have exclusive usage of that particular number for their protocols, for their services. Operating systems use those numbers as well. They're dynamic because these dynamic numbers are called dynamic because web browser opens up, let's say, port 60,000, sends traffic to port 443. 443 responds back to port 60,000. When the transfer is done, the browser closes its client service, and the port is closed. Open ports, when not needing to be open, represent vulnerabilities, ways into the system, if the way into the system is through the port. More on that another time. I know I'm running a drop late, so I'm going to try to wrap things up in a couple of seconds. And do we still have time for a Kahoot quiz? Or did I lose that opportunity? 20 questions? Okay. So where are these port numbers found? I told you that MAC addresses are found in frames. IP addresses are found in packets. Well, you know what? Inside of the frame is a packet. Inside the packet is one of these two things. Either a TCP segment, transmission control protocol segment, or a UDP, user datagram protocol, and we call it an actual datagram. They're very different. In fact, take a look at some of these pros and cons. TCP, if the sending application chooses to use this, TCP is guaranteed. You know, they lied to you. They said only death and taxes were guaranteed, but there's actually one more. Death, taxes, and TCP are all equally guaranteed. UDP is connectionless, and it's not guaranteed. TCP has all these bells and whistles with acknowledgement and sequencing, and UDP doesn't. So which one is better? And by the way, the common theme is that this is where port numbers are found in one of these TCP segments or UDP datagrams. Which one of these sounds better? TCP on the surface sounds better, but which one is actually better? The answer is something you'll be wearing when you're 90. Depends. Depends. Where integrity and accuracy is of great importance, like a file transfer or a web page or an email, you know what? We'll agree to some of that overhead, a lot of that overhead, all that overhead that TCP affords to get it right. But for streams, hey, look at our streams right over there. For streams, for real-time communication, we don't want the overhead that TCP will add. Because if you miss a few bits or if a few bits come incorrectly, who cares? You might notice a small degradation in sound, a small degradation in video, but it's a fleeting moment in time. It's not going to make a difference. So for those types of examples, and DNS and DHCP, major networking protocols, use UDP. DNS actually uses TCP for two niche cases that we won't talk about right now. There, it's better for speed than for integrity. Does that make sense? All right, so think of each of these markers as an actual message that needs to be sent. So think of these as actual messages that need to be sent. So that's how UDP works. In other words, the message is just sent. If it gets there, it gets there. If it doesn't get there, it doesn't get there. The sender doesn't know it didn't get there. The destination doesn't know what it didn't see. But would you agree that was pretty fast? That's pretty fast. That's how UDP works. Let me give you, in conclusion, the TCP version. Okay, you got some of them back? And just one more underneath there. Yeah. This doesn't happen in the world of networking. You never retrieve the UDP datagrams that you lost. Oh, that was a strong throw. So, what's your name? Jose. Jose, could you come on up just so you're on the stream? I don't know how well that came through on the stream, but I just was firing markers at him, and he had a real frightened look on his face. I do this in my classes as well at shorter range. So that was the UDP version. You got some of my message, but you lost some of that. Now, if it was a stream, you might have missed a second or two. The video might have gone down a little bit. The audio might have gone. Naked eye can't tell. Naked ear can't tell. Here's how TCP works. If I wanted this guaranteed, acknowledged, reliable delivery. Hi, Jose. I'm Jonathan. So say, hello. Hi, Jonathan. I'm Jose.
Hi, Jonathan. I'm Jose.
OK. I want to send you some markers. Can I send you some markers?
Yes.
And then you say, can I send you some stuff as well?
Can I send you some stuff as well?
Sure. So watch this, everybody. Come a little closer here. Well, let's make it some form of not direct delivery, but OK. So now tell me what you got.
I got a marker.
Now, by the way, that's not a reply. You know why that's not a reply? He's not replying to the message. What would you say that is? That's just an acknowledgement. I got the marker. That's an acknowledgement. So now I'm going to throw him the green marker. Now, wait a minute. I sent him the blue marker, and he told me he got the blue marker. I sent him the green marker, and he didn't tell me he got me the green marker. But you know what? No problem, because I put a copy of that marker in RAM. And if he doesn't tell me he got it in a certain amount of time, you know what I'm going to do? Send it again.
I got the green marker.
Do you see how this additional overhead is not really desired by real-time streaming applications, where it is absolutely what we want to do for email, file transfers, websites, things along those lines? Jose, is that pretty cool?
Yeah.
Give Jose a round of applause. Give Jose a round of applause. So that works with something called a TCP Three-Way Handshake, which is what we were doing over there. Hey, I'm Jonathan. Can I send you some information? Yes, Jonathan, I'm Jose. Can I send you some stuff as well? And then I say, let's rock. And after that, every time I send him something, he tells me he got it. And if he didn't tell me he got it, I just send it again. That's why TCP is as guaranteed as death and taxes at layer 4. That's where the port information is. So, did you follow me yet? So smash that subscribe button. Thank you very much. So do we have time for a Kahoot? I could put it online and let you do it asynchronously if you want. All right. Thank you, everybody, on the streams. And by the way, in the world of networking, the three-way handshake uses TCP flags. That's why the three-way handshake is affectionately known as SYN, SYNAC, ACK. And then at the end, the connection is closed in an orderly fashion. It actually takes 4 steps. FIN for final, finish. Technically, it's FINIS, the Latin word. FIN, ACK, FIN, ACK. And that's exactly what we are doing over here. Thank you. I am going to end my stream right now.